So, good morning. Let me start. So, first of all, I uploaded yesterday this lecture 8. That is the lecture that I didn't give last week, that I had to skip to do some emergency appointment. And then, and the topic there is a kind of again, a recapitulation of the previous lecture when I introduced the transformers technology as a kind of evolution of the recurrent neural network idea. And I went hopefully through a more kind of logical pathway. And then I also introduced the graph neural networks. Introduced and kind of concluded for the sake of this course, and I will just repeat the main point, and then today we go to representation. First, from a kind of more abstract point of view, what are representations in neural networks, and then leading to the idea of exploiting a representation of neural networks in order to generate instances of some population, so generative AI, even though I will basically just touch it with the autoencoders. I don't go deep into generative AI. And then I'll start with an overview of the representation that we actually use in chemistry and material science. So, from the point of view of the recurrent neural networks and the path to transformers, so basically the overall idea is that we start from in neural network architecture, that is the neural network architecture of recurrent networks, in which we have some input going to a network. So these boxes are always multi-layer perceptrons, so it's just a shorthand for a full-fledged deep network, in which we give some input at some point, and then we get some possible output, and then well, the letter H is used both for the state of the network and also what it is passed to the next instance of the network, right? So sometimes I use the small h to make it slightly more clear, and so these are the so the general idea of this recurrent network is that for every input, so we have in mind a sequence of inputs, and the new input goes into the network, so like the x1, but also the some output from the previous iteration. So what we are interested is as some specific output that is typically what we train the network on. So when I use y, I always have in mind that there is a loss function at some point that has the prediction minus the ground truth, and we want to minimize this kind of object here for also we have information on some output, and we want to make the prediction of the network as close as possible to the ground truth. While the inner state of the network is typically more complex, and we don't have a training, kind of information for it. So it's just what the network finds out in order to predict properly the y's at each step. So this is always important to remember. So So this is iterated over and over. And then we were focusing more specifically on the so-called many-to-many instance of so architecture of the network. So it is an instance in which we have first a kind of so-called encoding part, and then we have a decoding part. Where you have your inputs, and here you have your outputs. Also in the encoding there is some output, but it's typically disregarded. And so what it is important is the information going through the encoding, that it is transferred to the decoding, and then we have and the encoding is finished by some kind of end of sentence signal, and the decoding is triggered by an input that is called start of sentence. And I say sentence because the many-to-many kind of instantiation of a recurrent network has the kind of prototypical application transforming sentences into other sentences, so translation from one language, natural language, to another language, but also anything that looks like a prompting that is expressed more or less in natural language into an output that also is expressed as a natural language. It could also be that you have something more complex than just sentences. You could have as input tables, sentences, and plots, and you get out plots or something like that. But the general idea is that there is a logical sequence, if not really a time sequence in the encoding, and that is given in the decoding. And when one focuses on this kind of many-to-many recurrent networks, people introduce the mechanism of attention. So this is, I went in more detail last time. So last time in the lecture that I have uploaded, and kind of the thing to remember is this query key value technology. So that instead of using every time for the prediction of new outputs in the decoding the overall hidden state in the encoding and the one of the decoding, we have projections. So these QKV operators are projection of the states of the metric of the network that gives us some specific subset of information in the form of linear projection. So this state is a vector, right? So just keep in mind that it's just a numerical representation that has been trained to represent in the most useful way for the prediction the input. And I should stress all these. I mean, it is complicated, but it's not as complicated as it looks the first time. It's all a well laid out sequence of linear operations. All this hurdle is motivated by the fact that we want to have, we want to treat input signals for which we don't know the specified length, and to some extent its structure. So we just know that it is a sequence of symbols. In the jargon, they're called tokens because we just but we could call them symbols. It's just something, and it is important which symbol and which sequence. So that symbol is before or after another symbol is important and has to be encoded properly so that the network decodes. And all the machinery here is doing this automatically, in the sense that all these projection metrics are learned, so all coefficients in these, or elements in these projection matrices are learned during the training process in order to minimize the loss function at the end of the day. That's what it is always done. And then, so we have this attention. We had a multi-head attention, where we, instead of having just one query and one key and one value, we have several of them. And here the idea is that, okay, from a mathematical point of view, it's just going to one projection matrix for each, say, state of the metric of the network. You allow for many of them. From a mathematical point of view, from a computational implementation point of view, no big problem. Actually, very happy because you can parallelize this. You just have different projection metrics that you can do at the same time. From a kind of more understanding point of view, one can imagine that the overall state of the network is carrying all kind of information about your sentence. It could be any kind of grammatical information, any kind of semantic information, any kind of context information, if it is a text about any geography or history or whatever. So it has to keep in mind, in some sense, so in this many-dimensional representation, if it is a text about whatever, Napoleon, it keeps in mind something about the history of France, it keeps in mind the fact that it's a male character, so in French or in any other language you have to take into account he, his, and so on. All these kind of things are all embedded, and then there will be a projection that does the grammatical thing, because at some point it has to connect this, and another one that does the kind of context thing. So if it has to predict a sentence that makes sense about Napoleon, it has to keep in mind all these things at all levels. So multi-head attention, and then there is a kind of crucial step that is self-attention. Again, I go in more detail in the previous lecture, and I tried also to explain it a bit more the logic, the lecture just before the holidays, in which people realize that one can completely decouple the encoding from the decoding, and also do the all the operations in parallel. So basically one has the input, instead of giving input sequentially because the state of the network evolves step by step, so it has to have gone through all the steps before, otherwise the state is not carrying the right information. One can fully parallelize, so give the whole input and then have this kind of self-attention mechanism that keeps track of this of all the input at the same time, so and one can do the decoding also in parallel. So well, in particular, this step of the self-attention, this is when we start talking about transformers. That was introduced in the famous paper in 2015. So the paper is called "All You Need Is Attention," but it should be called self-attention. This is what they introduced in that particular paper. So this thing that you fully parallelize the training of the network and also the decoding, so the prediction, and making use of parallel computation. One can do it in real time. Yeah, okay. Then there is the multi-head self-attention, but it's hardly a novelty at this point, meaning that instead of having one specific projection, you learn many at a time. And then just to give ideas, do I have it still here somewhere? Yes. For say GPT-3, that is one of these model that use transformers. No, not the first one, of course. There's a 3, but GPT was the first to use this technology for natural language processing. So it has, say, just to give numbers, to have an order of magnitude, so the number of heads is an order of 100, like 96 of this, and overall you have order of billions, so more like 100 billions parameters that you train for the overall network. That it is certainly a lot, but let's say, compared to kind of possibly naive, fully connected multi-layer perceptron. I don't know if anybody has done the estimate how many order of magnitudes more of these parameters you would need in order to do this kind of, and just hope that just by giving sentences of different lengths and so on, the input, so the multi-layer perceptron kind of finds its way in this type of input and prediction space. Okay, so that's the kind of very short recapitulation of the transformer technology. And as I mentioned, probably in lecture before Christmas, so most of the applications so far, or let's say the widely spread applications of these methods are for so language processing, but there are many attempts or even successful attempts to use transformer technology, say, to predict crystal structures, molecules, by using, so the tokens will not be element of a sentence or of natural language, will be some pieces of information that are related to our chemical representation. I don't go too much into this. It's really a huge kind of a forest. There are many papers. The general drawback, and the main reason why I don't go through, is that if you apply it to specific subfields in chemistry, in material science, you see even more the problem that you have for the large language models, or the hallucinations, right? So basically, what the network is trained to do is to make predictions that make sense, where the make sense is specified clearly by the loss function. So you have to get close in this kind of vector space sense to outcomes that are in the training set, right? So the network infers that you should put together words in a certain way, and again, then there was the semantics and so on. But sometimes, or if not often, these actual outcomes make no sense from a semantic or actual point of view, because they were just categorized as similar in a mathematical sense, but not in the actual application sense. So with languages, maybe the problem is getting smaller and smaller, even because of people are using a lot of computer power and brain, human brain, to cope. In science, so far, I don't see much progress in that direction. So you have many publications where you say, okay, I predict new crystal structures, predict new chemicals, except then you have the minority report, or not so minority report, in which you have a lot of nonsense things. We know that networks hallucinates, but of course in science we want typically also to have some reliability on the system. Not saying that the technology is not reliable, it's just that there is much more work to do for getting to kind of scientific level prediction expectations. And then so let me go to graph neural networks, also introduced in this lecture that I uploaded. So the general idea is that even more general than the kind of input and output that we treat in transformers and language models, the kind of most general possible type of input or data structure that we that we may think of is a graph. A graph in sense of like the mathematical graph where we have vertices and some edges connecting the vertices. So what are the vertices and what are the edges? It is exactly what makes the application general enough. So any vertex could represent any item in a population. So it could be people in a company or overall humankind, or atoms in a system, and each of the vertices carry some kind of features or a description of that particular vertex. So if it's people, birth date, name, whatever. If it is atoms, species, its coordinates, and this kind of thing. So can you imagine? So you just attach information to the element of the population of choice, and the edges. So there is a connection between two edges if there is some kind of relationship to be specified, right? It could be if it is people friend with or relative of, and you don't even need to not even, I mean, this is a general thing because not all the vertices need to be of the same kind. So basically you could have vertices that are people and other vertices that are jobs. So you connect a person to a job. The usual example for a knowledge graph. So a graph where you really put together information about items. You would have, I don't know, a painting and a Mona Lisa. Then you have a relationship that is painted by Leonardo da Vinci. Leonardo da Vinci was born in Vinci, a city in Tuscany, and so you have nodes that are all this kind of concept, and the relationship is painted by, born in, the painting is in Paris, that is the capital of France, and you have each node, Paris, France, and you have different kind of relationship. And you could think to represent all this in one single graph, and in fact, the internet is just a huge graph of this kind, or could be represented as, and then via the hyperlinks, and so the benefit of thinking to represent data structures in graphs is that one can be as general as possible. So at some point you don't have to predetermine how much information you have for each node, how many nodes you have in this, or how many vertices you have in this graph. So you just generate what are the constraints. So if you have a kind of vertex of type atom, you would expect to have certain information and not other, but you don't necessarily expect to have all the information, right? So this is to be more general than just a tabular representation. So once you define or you resort to graph as data structures, you may ask, okay, what do I predict? So let's say when we go to inference on graphs, we have a node, same as vertex, level prediction or inference. So we have we train some model that will be in a second a neural network or a graph network on a graph or a set of graphs, and then we now say I have a node, a vertex for which I don't have information, so this XV, the information on that particular vertex is not known, but let's say I know the connection of this node, and then I can make predictions on the property of the node based on what? On the fact that I have information from the overall graph, and I expect that the model will learn that if the node has a certain number of vertices with this particular kind of type of vertices, and the neighbors, so the vertices that are connected to any vertex that with this kind of connection have this kind of property by themselves, so this vertex typically has that kind of properties. So let's say now if it is let's say again a person, you can infer what kind of job, or if it is again an atom, you can infer the coordinates that would be used for some kind of evolution of the system, for example. Then you have edge level inference. So you predict typically. So this prediction here could be regression. So you predict a value in this vector of properties, or a classification. So if this, I mean, some of the properties could be discrete, and so you can do a classification kind of inference. Typically, the edge level inference is a classification, meaning that is typically just to say, okay, is there an edge or not between two nodes of a certain kind, like an edge of a certain kind. And the prototypical example is, say, recommender for movies or clothes, and historically is the reason they were developed, this kind of networks or models. So if given that certain items, movies or clothes are connected with each other because people like them both or buy them both, then you have a new item and say, is this item actually connected to the other ones because of properties that it has and so on, right? So you infer if there is or not an edge, and then you have a full graph. So a prediction, I put a sub, so you just make an overall prediction over the whole graph. So it could be again a regression or a classification over the whole graph, and then you have another one that I say in a second. So I think here the easiest example is if your overall graph is a molecule, then it's kind of obvious to understand what you mean, a prediction over the whole graph. So you make a prediction on the property of the overall molecule. So in your training you will have, but this kind of graph you will have this property, whatever, if it is a useful drug or not for a certain treatment. And then you would have another graph, and then you have to say if it is similar enough to that other graph that you've used in training in order to make a prediction if it is a good drug or not, or if it has any other property, some continuous property of interest. So what is basically saying that there is a kind of graph matching task or inference. So what one is doing when doing a prediction on a graph is, first of all, the model has to assess whether two graphs, one in training and one in test, they are similar in some sense, right? And it has also a kind of abstract, so besides thinking about molecules, in general you want to compare graphs and say, are they similar? Graph comparison, naive way, is the typical NP-hard thing. You would need to take all the nodes and try all the permutations of all the nodes in both pairs in order to see if there is a matching node by node. So if the connectivity is the same, then you conclude the graph is the same. But even if there's one node or edge that is different, then you have to find a matrix that says in which sense two graphs are almost the same and two are completely different, right? And you would like to have a model that does this kind of matching kind of automatically. So by just training over a data set. So the type of operations that, or the kind of conceptual representing a general graph. So, believe it or not, this is a very general graph into a neural network in order to make predictions. So we have the general idea is to do graph embedding. So in general, so remember, for example, we went from say images through a convolutional neural network. What we had at the end, so we had this sequence of convolutional filters that we kind of could make sense of, thinking about actual filters, so Photoshop-like filters that you apply to the image. And so you go through a sequence of these operations, and you start from a matrix that is your image, possibly a stack of matrices, different channels, and so on. So a tensor. And then you have a transformation, that is our embedding. The convolutional network has done that in order to, so the embedding was optimized in order to make some prediction on the picture. Is the picture containing certain features or not, or also some kind of regression. So if you want to evaluate whatever scalar property that could be attached to a picture, especially if it is some kind of spectrum that you measure in some experiment. And then we went through, so after the embedding, so you could split the overall convolutional network in a set of convolutional layers. Then there is a representation that is now a vector that is the kind of the embedding, not kind of, it is the embedding of the image. And then there is originally a few layers of a multi-layer perceptron that gives our prediction, right? So keep in mind that this is an overall recurrent idea in deep learning. So you have some clever way to embed your information that could be of any kind in the input. Could be image, could be a sentence, and then you have it embedded in the proper way. And then at the end there is some multi-layer perceptron, because at the end of the day you still have some vector representation, and you want to get an answer out of it, some prediction. So for graphs, we also have the same idea. So we have the graph, then there will be some kind of graph convolution network, and then you have some embedding as an outcome of this, and this goes to an LP, and then you make prediction on the graph. So the point is that we want to find to design architecture that could take essentially any graph on the left side and embeds it. So for images, we had this point that we constructed a convolutional layer with this specific idea that the representation had to be translational invariant with respect to the signal that we were looking for, right? So we are looking for some kind of feature in image, some local pattern in your microscopy image, and you want to train the network such that it will detect that particular pattern everywhere in the image. So you don't have to prepare exactly the image so that the pattern is in the center, because otherwise you would need to already know if it is there or not. So we design the overall graph network, the overall convolution network to be translation invariant. So also for the graph network, we need to impose some constraint. So let's say mathematically a graph could be readily represented as some kind of graph. Is basically specified as something that depends on its vertices and the edges. And we have, we can represent mathematically as a composition or juxtaposition of concatenation, maybe, of adjacency. Adjacent. something like that. Adjacent. I have no idea how to write it. Adjacent matrix. Plus features in this way. So let's say that each row here would be a vertex, a node, and then you would have, so vertex 1, 2, 3, and then you have again the vertices, and then the adjacency matrix part is okay, node with same node, there is typically no connection. So if you go to this graph, there is a connection between 1 and 2, 1 and 3, and not 2 and 3, right? So the adjacency would be 1, 0. So you put a 1 if there is an edge, and if you put a 0 if there is no edge. You could generalize. There are edges of different type. You put different numbers there to categorize which kind of edges there is no edge. And then you have your features, right? So this would be x feature x1, x2, x3. So it would be coordinates of the vertex. And so on and so forth, right? So you, for each vertex, you would have his connectivity with the other vertices. So this is fixed dimension, right? The moment you have the graph, you have how many dimensions you have here, and then you have also how many dimensions you have here. So this here would be a representation of the overall graph, and the first thing that should come to mind is that this representation is not very convenient because it is not permutation invariant with respect to the labeling of the vertices, right? So the minimal thing, constraint that we want to apply to a representation for a graph is that it doesn't matter its embedding and therefore its properties. It doesn't depend on the order with which I label the vertices. But of course, I need some order if I have to transfer the information. So what we want is that this ordering is lost in the embedding. And also not very evident from here because we would have the number of columns here that change with the number of vertices in a graph. We want to, but in any case, we want to have a representation that is also independent. I mean, this representation by all means is depending on the number of the size of the graph, the number of vertices. But eventually, we want a representation that is also not depending on that size, and the general. So I went a little bit more into detail in the uploaded lecture. So the general idea is that we build embedding of a graph in layers, and so let's say if we look at use this kind of graph here. T, and then I have a C that it is connected to E and F. Doesn't really matter. The point is that I want to look at this graph and I want to make an embedding, say, for the node A. I expect that this embedding depends on the node itself and its neighbors. So it would be B, C, and D, yeah. And in turn, I expect that the information that I use from B, C, and D that is used to construct the embedding of A depends on their neighbor, right? So B would depend on A and C a lot, A, B, F, A, B, E, F, D only on A, right? So this is kind of the motivation. So we want a representation, an embedding of the first of each node of the graph, and then I have a overall embedding for the graph, such that this embedding is aware of the connectivity of the graph. So, and I do that by saying, okay, I have information coming from the neighbors, and the information coming from neighbors coming from their neighbors, and so on and so forth. And this leads to the kind of graph convolution embedding. So we say that we have a network in which the state, okay, I write it like this. So yeah, I must say first of all that so there is an index k here. So the representation for the node at say level 0 is the input. So it's this x of I. It's this. So it's this information that I have from my graph, from my original data, and then I do this kind of iterative procedure in which I take the embedding at each layer. I construct a so-called message. Sorry, this is a bit fast, but it's the core of the other lecture. So basically, I take layers of embeddings from 0 to a final number of some specification, and I iterate this kind of projection of the state with some kind of metrics. And what I do with this projection, I combine them over all the so J that belong to the neighborhood of I, right? So the embedding of I depends on the embedding of the neighbors. Normalized by the number of neighbors, and this is where the size independence comes in. And then I want also to have some kind of information coming from the node itself. Typically here is a B, but not the huge. Sorry, I'm missing. And then there is some kind of activation function. So this is built in this way. So there is an embedding that, again, at step 0 is the actual information that you have on the node from your data. Then it is projected by to-be-learned metrics. And when I do this, overall, I call it aggregation. So we have, in the literature, it is identified as 2 steps. We have a message passing from neighbors and an aggregation of these messages that are passed from the neighbors. So that's also, you typically find graph networks described as message passing graph networks. And so then you do this, and so evaluate the state as this activation function of some linear, properly defined linear transformation from the previous layer. So when I say layer, is because, so when you look at this representation here, the embedding of A depends on itself and the neighbors. Neighbors depends on, well, each of them is also itself, right? This is structured, this graph is more or less intentionally represented as a neural network in itself, and this is what we are building here. So this is a neural network in which you have your input, X, then you do a transformation to the first layer, linear transformation, and then activation to the second layer, and so on and so forth. So the number of steps here is the number of layers in your graph convolutional network. The kind of operation that you do is almost the same as in a multi-layer perceptron. So you combine information from the previous nodes, but they have to be constructed in a proper way. So let's say this is an example. This is an average, and it is taken as, so this is a kind of simple example to take something that it is permutation invariant. So it doesn't depend on the number of, so the way you label your nodes, and also size independent. So it doesn't depend how many neighbors as each node. You will just for each node you will just get a kind of consistently defined message passing and aggregation operation, right? So this will take your information, your initial X, will warp it by means of this projection matrix. This is another projection matrix specific to, so it's the node with itself, to the next layer. So aggregation, activation function. So at the end you have some H, and the final, say, Hn has to be aggregated over the graph. So again, there is some kind of averaging, or it doesn't, it's some operation that will look a bit like this. I don't go into much detail, but then this information go into so I keep it different because you could make inference on nodes, right? So you don't need to aggregate over the whole nodes. So if you want to do on the graph, you aggregate over all the nodes in the graph, and then you pass it to the some multi-layer perceptron and make the prediction, right? So you present to the multi-layer perceptron an embedding of the graph that is now independent of all the things that you don't want it to be dependent on, and do the final prediction. So I would like to stress this is over and over the same idea. In principle, our multi-layer perceptron is such that with enough nodes and layers is able to predict any possible function of the input. But we construct this convolution transformers in order to embed constraints or properties that we want the embedding to have, so that at the end you just have a much smaller multi-layer perceptron, but at the end you always have this multi-layer perceptron, right? That does the overall learning. So here, of course, in the overall learning, during the learning, one will learn these coefficients here and these other coefficients here, right? This is what the network is actually doing. And to connect to the multi-layer perceptron lectures, it is always done by backpropagation and gradient descent, right? So it's always like, okay, I have a set of inputs, I have certain prediction. Now, if I change my coefficients in all the matrices all around, how much my prediction changes, is my loss function decreasing or increasing? So I construct the path in the coefficient space so that I always decrease my loss function, right? So eventually one has to sit down and evaluate all the gradients with respect to all the weights. That is, of course, for a multi-layer perceptron is almost trivial. For this kind of complex convolution network, it gets more and more complicated. But at the end, it is just an algorithm that one can write down. And the last point that I touched last time was you go from graph convolution networks to graph attention networks. So this technology would be like the most general that you can think of, right? So essentially everything now is mapped into a graph attention network. So the most simple, kind of just to understand what one is aiming at, is so we have this kind of aggregation in a convolution network. And the first thing, especially after you have been primed by the concept of transformers, is, why do I have to do the same operation over all the nodes that are neighbors to I, right? So I go over all the neighbors, I take the state from each neighbor, and I just average it. Or other possible operation is some kind of softmax, for example. I take then you can say, probably each node, depending also on the type of edge, will have some different kind of information that is useful to make a prediction on that node or on the overall graph. And so basically you say, okay, I have the general framework that is the same, but now, so I have also the idea of a passing of information. So hi, hj, okay. But instead of just averaging, and I now have some coefficients. So these are attention coefficients. So that yeah, the alpha ij are bigger than 0, and the sum of the alpha ij's over j is equal 1. So I really, so similar to the attention in a recurrent network, and this is why they're called exactly the same, is just basically I try to weigh the information coming from the other nodes. And then what I'm learning now are these coefficients alpha I, j. Of course, I'm increasing complexity, but I gain that I have more flexibility to make predictions. So I could make a prediction at different levels, and then, okay, here, the self interaction is included. They say that we consider also alpha ii as part of the thing that we calculate, so we don't have to rewrite it. So this is, I just wanted to say, in this very kind of compact representation, we have the gist of all modern graph network implementation, right? So basically, we start from any information that we have on our graph, information on the connectivity, and then we learn this embedded representation in this most general way, almost the most general, train the projection matrix, the attention coefficients to the task that we want to attempt, and then we have our general network. Okay, so what time is it? Let me go to representations. So from a general point of view of neural networks, so we saw that in a kind of the general classification problem, let's say that you originally you have your data that are represented in any number of dimensions, and so we want to just classify if our data represented in this original dimensionality, they belong or not to the shaded areas, right? And so one can prove that with just 2 layers, actually, you can, hidden layers, you can construct a network that learns this kind of classification problem. So we have a network that starts from the initial representation. Here is 2-dimensional, so you have your x1, x2. So you just give x1, x2. Then something happens, and then you have basically a classification node that says yes or no, if you are in the shaded area or not. So in between there are layers. Say here I have in mind a kind of fully connected thing, right? So and so on and so forth. And in each layer, basically, when you, after the training, and you have trained your weights, you would have that your x is transformed into, they were called z, right? So that we have the z, say, 1. The Z0 is the input representation. At some point you arrive to the Zn. So your input will be represented at each layer as a set of coordinates, right? Because it will pass through the transformations, and the outcome is a number. So at each node will have a number that will represent the input. So you go through this transformation that, of course, could change the dimensionality. Point I want to make here is that since the last layer is just an activation function, right? So remember that the neuron is always doing just this aggregation, or let's say affine transformation. The offset is normally inside the representation itself, and then there is an activation. So at the end it says either 0, 1, or maybe a smooth number between 0 and 1. If it is 0 and 1, they are perfect classification, or you get the probability to get classified or not. So point here is that one way or another, since the last activation is linear, because it will just say if this linear transformation is smaller than, then no activation. If it is bigger than, then there is activation. So by necessity, the network has to learn some kind of map that goes from this as complicated as it can be at the beginning, kind of boundaries, to a linear boundary. So they say, for example, the shaded area will be completely mapped into one half plane, and the unshaded area will be in the other half plane. So this is what the network is always doing. And so we kind of know that at some point we have this final representation that has this linear mapping feature. Now, afterwards, after I have this representation, so what happens if now I take in this kind of representation space a point that it is here or there? So I know already this classification, right? So because I have learned this classification, and I know that if I select a point here, it will be shaded, and here not shaded. Now, what if I could go back? I mean, I could go back from this representation to the initial representation, and therefore I could basically use this representation in order to generate new data points, because the question could be, okay, now give me a data point that belongs to the shaded area, not just I give you a data point and you tell me if it is there or not. So I mean, the way this is laid down, the inversion from the Zn to the Z0 or the X is not in general possible. But then people could say, okay, let's say that I have layers, my representation, and now I put layers, and I go back. So I learn the inversion, right? So this is my X, this is my Z, and then I go back to X. So this is MLP, and this is MLP. So this kind of task in which I give an input, I give the architecture of the network, in particular where there will be a layer of interest called latent space. I mean, every layer is a latent space, but let's say there is one particular that we are interested in using afterwards, and then we go back to the original. Of course, the input typically does not have the same dimensionality as the latent space representation, and so basically, if we construct such a network, we want to find, so our cost function would be in this way. So basically I have my input X, and I want that the projection of the input into, so this would be our Z, and then the projection back, so this is as close as possible to 0. So I have a loss function that it is some projection and then some back projection, and I want that this overall operation is essentially as close as possible to unity. Of course, here I have a bit cunningly written already as WW transpose, because I want to make immediately the connection that if this W is really just a linear operator, I know that it's just take the transpose, I'm doing the inversion, and this is known as principal component analysis. Right, so I could design. So you've seen in the basic machine learning course that you can immediately write down how W looks like. This correlation matrix between the data points, and then so. Solving it as a linear network, it is completely pointless, but you could design an architecture in which you have all this connection. Actually, you need only one layer, and then you project into the latent space and then project back, and then you're learning these coefficients here, W, in these two linear kind of layers of a linear network. In literature, so especially theoretical literature, you see a lot of this linear neural network that is, of course, of no practical use, because always you can solve the problem in a closed form. It's just a regression problem every time. But to kind of fix the ideas, one starts reasoning about these linear networks, and then say, then there is no linearity. That in mathematics is always like, then I don't know what to do. And then you need some kind of, I mean, at least local reasoning, right? So all this is to say yes. So then if I have this kind of machinery, I can generate data points that are, let's say, uniformly distributed. So I'm doing the classification, and then I know that I would get points that are classified the same. So here I didn't say, so here I'm just doing the inversion, so I need to kind of connect this Z to actually making a prediction over Z, right? So I have to combine and make a more complicated architecture if I want really to address this problem that I started with. But imagine that you can do, I mean, you have a task in which you want to have the possibility to invert your representation, but at the same time you want that the representation is such that you make some predictions of your right, like this, that you have this kind of prediction. Okay. I started from this because then I want to go a bit, so let's consider nonlinear networks, and then in general we have the problems, the task to kind of generate this representation, and like the symbology is typically like with this trapezoidal kind of representation in which you say I enter X, I give out X, and I learn the dimension, and the kind of trapezoidal shape is to say that in general the dimensionality of the latent space is smaller than the one of the input. And what I'm trying to do is to say, okay, if I have points that in my original space that are distributed in some way like this one, I want to learn a representation that is, I mean, to reduce the dimension you have to go to 1, so that if I select from this coordinate z, I then have, say, I would have a point that lies on this line where you see almost, it explains all the variance of the original point, and then I add some noise in order to find points that are meaningfully representing points in the original distribution, right? So the idea is that I get this embedding by just looking at the distribution of these points. So I train, in this case it's still a principal component analysis, it's still linear, and then I just take one point from the Z representation for which I know exactly its transformation into the new point, but let's say that I add some noise to that point in the other direction, and then I kind of expect that I have a point in the other, so that is representative of the population. So let's say first step, you want to say I want to actually do this in the general nonlinear scenario, right? So let's say that now your points, maybe this I should have prepared. It's always difficult to draw these points. That actually, basically, you would have some kind of again, if your initial unlikely representation is in 2 dimensions and the points are arranged in this spiral, you want to predict point on this spiral. So you want the network to learn the spiral, and I hope you believe that if you just introduce known linearities in this kind of architecture, you can learn also. So your Z that you learn in between by just mapping in and out from this initial distribution of points will be representative of the actual distribution of the points in the original representation. So. Yeah.
So is it still? Can I still imagine that something like PC is just now extended for not only straight lines but also?
Yeah, absolutely. It is actually also that one you can solve without a neural network. It's called kernel PCA. You just try to kind of guess a little bit which type of nonlinearities you build the kernel, and then you actually you just need to define if points are close by or not close by, and then you can do this with the so-called kernel PCA, and then the literature is full of examples in which you just complicate a little bit this shape, and your kernel will not reconstruct it, but then you construct another kernel that will work, and then so on and so forth. And then people got bored of this, and they say, okay, but the neural network is doing that for me. I just design the architecture, and then I train it, and it will find the representation. In order to get, so what I have here is called, I should have said before, autoencoder. So in general, we have this idea. We go to an encoding. So this part here would be called the encoder, and this part would be the decoder. And then if I go back to the original representation, we have the so-called autoencoder. And then we have one more step to go to the kind of ground state, the basis for a generative network. So if I just train a problem a little bit like this, so basically instead of being, so I have that I just want my x and x to be as close as possible. So I construct a loss function that it is just the difference between x, and then I give the architecture and I train my network. So first of all, one should note that there would be not only one way to do this. Also, one has to note that the problem is basically, the quality of the problem is defined by the dimensionality of this encoding, the Z kind of representation. So it makes sense to have so let's look at this example here. It makes sense to have a one-dimensional representation only if your data are actually distributed as something that goes around a one-dimensional manifold plus some noise. So the key word here is noise, right? So and it's also the fact that when you go back and you select one point here, you want to say, okay, I pick up one point in this one dimension representation. I invert it and I add some noise. So and I expect that I find always a point that it is part of the initial population. So be it coordinates or chemical species or be it pictures. So there is one extra requirement before we arrive at the so-called variational autoencoder. That is, let's say I shape the noise. So basically I impose, I want to impose that whatever is the original distribution, right? So I have my points. There is an underlying distribution, right? So I have a probability of x1 and x2, right? So I know that, I assume that there is an underlying probability distribution, and that is somewhat what the model is trying to learn. So there is a certain probability distribution. It is mapped into a latent space representation, and then I reconstruct this probability distribution, because if I sample from the latent representation, I am able to produce data points that belong exactly to the original distribution. So I basically impose that the distribution in the latent space is one I know. So I just say, okay, out of all possible representation, because I have degrees of freedom that I can have from going from x to x back, I choose one that gives a given distribution for the latent representation. I mean, in the linear PCA, I was looking. I mean, not evident from this, but the principal component analysis out of many possible representation is the one that preserves the variance of the initial data, right? So it's the one that maximizes the reconstructed variance of the initial data. Here I want to impose actually the distribution in the latent space, and then this leads me already to so basically our Lagrangian, loss function would be also some kind of distance. So a distance between. So I want to minimize this distance, but then I also want that the distance between the actual distribution and some distribution I know is minimized. So I select, unsurprisingly, a Gaussian. So I want that a Gaussian with the average equals 0 and whatever sigma equal 1. So this is a normal Gaussian. So I want that this distribution of in the latent space is as close as possible to this Gaussian. For this I use the Kullback-Leibler divergence, so some measure of how different I am from a target distribution. And then there is a coefficient here. So by now you should be immediately recognize that something that looks like some kind of error plus some kind of other constraint with the coefficient. Well, first of all, it is the Lagrangian, but the computer scientists do not know about Lagrangians. They have loss function. So this is a kind of regularized expression. So basically, out of all possible representation that we could have, we are choosing the one that from which the latent space representation is as close as possible to a Gaussian. And so why this is useful? Okay, because then once I have trained my network, I just pick up a random number with Gaussian distribution, and then I use the decoder of the network in order to get the new data point from the original distribution. And again, originally it was done for images. You get a new images of a cat that nobody has ever seen before, but still looks like a cat. But also have been extensively used, say, to predict crystal structures, molecules. It's really, maybe you have a representation that is a graph, and then you build a graph network that is actually an autoencoder, so you have this internal representation, and then it will produce new molecules that have a certain that would belong to a certain class, so that you could then try to synthesize and so on. Yeah.
Or maybe also, I guess, create some structures of a given but the same molecule.
Or a new structure of the same molecule. Yes, that also all depend on the task that you train the network on. Yes. And so the numerical complication here is that the more the original distribution does not look like, say, a multivariate Gaussian, the more this training is cumbersome, to the point that sometimes it really never converges. There is always a solution, but it may never be found, or a kind of a good solution by the network. So what people actually do to have really generative kind of artificial intelligence, you have a chain of this kind of transformation. So basically, you impose in steps that you go to this Gaussian distribution, and then you go back, but you always target. You need a distribution in the very center of the network, that it is something you can sample. And typically Gaussian. It could be uniform, but it's a little bit more cumbersome to define because it's sharp edges, so you like this kind of decay in the distribution. And then you do so so when you do this chain, in some sense, I don't want to specify here, chain of autoencoders. You get to the diffusion model. Diffusion. Yeah. So diffusion models can be explained as a proper chain of these autoencoders that go from the original representation down to the Gaussian and then back. Dolly was the original image generation thing was so the image generation part was a diffusion model, so this chain of autoencoders plus, of course, a language model, because you got from caption to image generation. So it had to map to images that are similar to the one you are describing in the caption, and then generate a random image that, or portion of an image that would be consistent with that, and do it over and over. Right. So, but in general, okay, forget about the caption. But in general, you give a certain set of images, and then you would generate new images, and so on and so forth. So these are all based on this. So I wanted just to give the general idea that is behind. So we start from compressing a representation. You can compress a representation, of course, only if intrinsically you have that your data live on a lower manifold than the original one. For images, that is pretty obvious, because you could just think it as a bitmap, and basically, if you give random values to the intensity, so even black and white of pixel, in the overwhelming majority of the case, you get what we perceive as white noise, or noise in general. So some kind of so the actual images, all the possible images in the universe live on a very, very small, so very narrow manifold that you can represent with the whatever n by m pixel representation, right? So the task is to find this manifold so that when you generate a new instance, you will map it back to something that looks like an image. I mean, also there we know the artifacts, but they are getting better and better also in that way, because the noise is modeled better and better. So from new images, you just have more ideas on how you model the noise. Okay. So let me just introduce what I wanted to say about. So I want to now. So I started talking about representations. Here in general, what is a representation in a neural network? In short, it is how the input it is transformed in any layer of the network, right? So here so I want to talk about representation in chemistry and material science. And what I'm actually after here is initial representation, meaning the following. So we want to present our molecules, materials, chemical physical systems in a way that the model class can treat, right? So now I will focus essentially on deep networks, even though the overall reasoning doesn't change if you use different model classes. And actually, I wanted to say one thing. So basically, if we go back to the general plan for the course, so basically I am moving away from the deep learning in terms of representation of model classes, and the bridge is through descriptors. So the next part of until the end of the course, I will be more looking into it's called data light kind of models, where you don't need a huge data set to be trained, when you do a lot of design on the model class in order to reduce the number of effectively training parameters, and the bridge is to talk about descriptors that would work with both the deep learning and the sparse method that I will talk about in the near future. Right. So yeah. So we could always say, yeah, okay, I have if I have a molecule, nothing forbids me to represent it to any model as a set of atoms that have certain coordinates, right? And say, let's focus on a molecule. Of course, one can immediately say, yeah, okay, but we know much more about the molecule than just a list of atoms. And first of all, we know that it doesn't matter the order we present, and then also, especially for more simple molecules or organic molecules in general, you can define if there are bonds or not, so covalent bonds or other type of bonds among the atoms, and you want to keep track of this. So you probably would like to already give this kind of information, right? Assuming that you know for sure that certain property are kind of easy to evaluate. So in general, we want to have representations that so let's put it this way, include known invariants. Right, so we want to have from the start, you want to say, okay, I have a representation that takes into account that the property that I'm measuring, for example, do not depend on translation and rotation of my system of atoms, right? So if there is no external field, it should not. And kind of very pragmatic approach is not forbidden, and people have also been doing that. You just say, okay, it's called, so the opposite of including the invariances is doing so-called data augmentation. You just take your system and then you translate it around and you rotate it around and you give over the overdue data, and then just, this doesn't cost anything from the point of view of data generation because you know that the property is exactly the same. And you just try to hint at the model that, okay, there is translation and rotation invariance because every time I translate and rotate all the coordinates, nothing changes. So you just, but yeah, one can show that of course this is exploring the complexity of your model for no reasons, because you could already work on a representation that is invariant for this kind of thing. So so most notably would be, well, never forget about the permutation invariant. So the order at which you label the atoms that doesn't matter, and then you would have well, rotation, translations, and any other kind of invariant that you may need in that particular problem. So then you would like to have a representation that is somewhat the general term people use is locally stable. So it is the general idea that similar input into a similar representation. So a representation, one way or another, it will be a vector. So the similarity in the representation with some kind of dot product or yeah, cosine, the distance between two vectors. The similar in the input, of course, it's a bit more problem dependent, right? So you would like that two molecules that have similar properties are mapped into similar vectors, or if not the same molecule, it's just vibrating, right? You want to capture, for example, the vibrational spectrum, so you want that it is preserved, that the representation of it is close by in the representation space, right? At the same time, you want uniqueness. You want uniqueness because you don't want that two different data points, two different molecules are mapped into exactly the same descriptor, right? So you need similarity, but you also do not want to. This is a kind of something I would say it's a little bit on the weak side. It's not a global. So you could have situations in which, in fact, two data points are mapped into the same because effectively they are the same, right? So let's say now you're making predictions about a property of a molecular crystal in the ground state. Maybe you don't need to capture the slight kind of variations around the ground state. If you're going from coordinates to your representation, you would say, okay, it's the same ground state. So provided that you're mapping to the right ground state, you could say my representation is actually the same as for the minimum of my potential. So this uniqueness is to be kept in mind, but it might be not the general. So a strong constraint. What it is important so is size dependence. So basically, typically for molecule, well, okay, it could be. So if you have a polymer, So you want your representation of a polymer, for example, to be independent of how many monomers you have in your polymer. So basically, you just want to capture the representation by the monomer kind of composition and structure. More clearly, if you are looking into bulk material, you don't want your representation that it is changing when you say the amount of atoms that you're looking at, right? So you look at the 1 supercell of diamond or 1 billion supercell of diamond, your representation should not change when you change the size. So there should be size consistency, well, not dependence, sorry, consistency. Otherwise, as it has been done, there are models that are trained on the unit cell. So you have to recognize the unit cell before you go to the representation and so on and so forth. And then everything that is beyond one unit cell is not captured at all if you have vacancies, interactions, and this kind of thing. And then, this is a practical requirement, computational complexity. Smaller than property, and then I explain what I mean. So, in general, you will have your molecules or data points represented in some convenient way, and we will do some mathematical operations on the initial representation that I get from my database in order to have my representation for my machine learning model. So essentially, I'm allowed to do any kind of complex operation on this initial representation, except that it doesn't make sense if the complexity, the computational cost of that operation to create a representation is of the order of calculating the property or evaluating in some other way the property that we are after, right? So the obvious thing is that, you have some atomic species and coordinates in a box, and you want to evaluate some elastic property of that system, and you have to calculate, say, from density functional theory, the descriptor. Basically, your model is based on the electron density, for example. Then you say, okay, once I've calculated my electron density, basically, I probably can calculate my elastic properties, so say, the bulk modulus, to make it simple, with very little extra effort. So basically, if my descriptor is the electron density, it's a nice model, but completely useless from a practical point of view. So I need that maybe I have an approximation to the electron density rather than the fully converged, say, electron density, right? So this has to be kept in mind, because sometimes, I mean, some models are pretty complex, and one should always keep in mind some machine learning model that they are simpler than the direct calculation, let's say. Okay, so I will stop here for today, and then I basically restart with this representation, because what I want to go is to make a more classification of which type of representation so the community has been using. So I will really go to the literature of the last, let's say, the first thing that looks like a representation for machine learning is from 2007. It was a paper for neural network potential from Beller and Parinello. It's more or less what you could say the modern birth of machine learning for materials and chemistry, and so I will go, I mean, of course, quickly through the relevant things that have been introduced in literature. Okay, so yeah, thank you for your attention.